This is May-June 2022, variant 21. We have nitrogen molecules. They are connected together by a strong triple bond. And as we know, triple bond is made up of 2 pi bonds and also 1 sigma bonds. And in order for you to have 2 pi bonds and also 1 sigma bonds, the hybridization, it must be sp hybridization. For any sigma bonds, we know that the bond, the orbital, it must be overlapping head-on, such as like this. And special case for any pi bond, it must be p orbital overlapping sideways. Nitrogen dioxide and also nitrogen oxide, which are being released from the combustion engines, will lead to the formation of photochemical smoke. So this photochemical smoke is produced when these nitrogen oxides react with unburned hydrocarbon. And from this reaction, it will form, in short, we call it PAN. And remember, for catalytic converter, the main objective is to convert the nitrogen monoxide and also carbon monoxide into carbon dioxide and also nitrogen. Where this nitrogen monoxide, it can cause photochemical smoke, while carbon monoxide, it can cause carbon monoxide poisoning. In the next question, we want to produce ammonia, but it's very difficult to produce from nitrogen because it is very unreactive. So how to produce ammonia from ammonium chloride? So we know that ammonium chloride is an acid. So if we add this acid to any base, a strong base, so it will produce salt, water, and also ammonia, which is, this is what we wanted to produce. So we can choose any strong base, for example, sodium hydroxide, or a group 2 hydroxide, for example, calcium hydroxide. 25 cm³ of 0.1 molarity of HCl is added to a beaker and the pH is recorded. So you might not learn this while you are in AS, but we can see that the pH for 0.1 molarity of HCl is around 1. And then we add 50 cm³ of 0.1 molarity of ammonia, and extra information is given where HCl is a strong bronze lauric acid. So the meaning to a strong bronze lauric acid is a substance that is a proton donor that is able to dissociate completely in aqueous solution. While it says here that your ammonia is a weak base. So a weak base is a substance that partially dissociates. So for any weak acid or weak bases, we will use a reversible arrow to indicate that the dissociation is incomplete. So ammonia in water, so ammonia becoming a base, so it will accept proton, so it will form ammonium ion. And water, what's left is hydroxide ion. So here we need to sketch a graph to show the change in pH when ammonia is added to HCl. So the initial pH, we started with the initial pH of hydrochloric acid, HCl, which is here. So the pH is around 1. But if you don't know how to calculate the pH yet, just know that HCl is a strong acid. So it means that the pH will be around from 0 to 2. So since the added ammonia is in excess, where we use 50 cm³ of ammonia, so the final pH at the end of the titration, that will be the pH of ammonia. So since ammonia is a weak base, so for a weak base, you will have around 9 to 12 of pH, where in this case specifically it's actually ammonia, the pH will be 11. So that will be the final pH. So for any titration involving a strong acid and also a weak base, you will have an equivalent point where the pH will be in acidic region. So you can memorize that the pH will be around 5. So what is the volume at this pH? What is the volume at this pH of equivalent point? So as you can see here, if we draw the balance equation for this reaction, so we have 1 HCl reacting with 1 ammonia to form the product. So since the ratio of HCl to ammonia is 1 to 1, it means that if HCl is the limiting reagent and the molarity for both ammonia and also HCl is the same, so the volume of ammonia where it changes color will be equivalent to the volume of HCl, which is 25. So to put that simply, I will say that I will have an initial pH at 1 and my final pH will be at around 11, which is around here. And I need to have a vertical portion of the curve at volume of 25, where the pH is about 5. So I'll start at 1, increasing, so the vertical portion at 25 and pH of around 5, and it will end at pH of 11. Okay, so straight to question 3. So this molecule of tea smells like lemon. And this molecule exists as a pair of stereoisomers. So under stereoisomers, so we have two types, which is geometrical, where this is the part where you have your cis-trans isomerism. And another one we have optical. This is where when you have a chiral center. So in order for you to have a cis-trans isomerism, you need to have a double bond, which we do. But the carbon in between the C double bond C must be connected to a two different group of atoms. And that one is applicable for this one, but for this carbon, they are connected to the same group of atoms, which is CH3. So note there is no cis-trans isomerism. And for optical isomerism, this is where the carbon is connected to a four different group of atoms. And if we see this carbon, this particular carbon, so on the left hand side we have this long alkyl group, and on the right side we have a different type of alkyl group. At the top we have CH3, and at the bottom we have hydrogen. So it means that this carbon is a chiral center. So since they have a chiral center, it means that it contains optical isomerism. So in this reaction, this molecule is heated under reflux with excess of acidified concentrated potassium manganate. We know that KMnO4 is an oxidizing agent where it will oxidize both of our aldehyde and also alkene. And obviously our aldehyde will be oxidized into carboxylic acid. Since it is so simple, let's put it aside first. So let's talk about alkene. So what happened here is when alkene is subjected to acidified potassium manganate and heated, the C double bond C will be broken. So let's talk about on the left hand side first, this alkyl group. So initially there is a C double bond C, but then the C double bond C has been broken. So you are left with C, H3, CH3, something like that. And if we look at this carbon, so this carbon is connected to two alkyl group. So if that carbon is connected to two alkyl group, it means that it will be oxidized into a ketone. So we will have C double bond O. So that would be the first organic product. So let's talk about what happened on the right hand side here. So initially you have C double bond C and you have many alkyl group, this part. So I just put it R, and we also have hydrogen because we need to complete 4 bonds for each carbon. And this C double bond C has been broken, so you are left with something like this. So let's talk about this carbon. So this carbon is connected to one alkyl group. So for any carbon that has one alkyl group, it will be oxidized into aldehyde. So it means that you will have something like this. But as we know, all aldehyde will be further oxidized into carboxylic acid. Means that you will have something like this. And obviously, just like we have mentioned earlier, that this aldehyde will be oxidized into carboxylic acid as well. So this part form carboxylic acid, this part also form carboxylic acid. So we will have something like this as the organic product. In this next question, we have molecules T undergo two types of reaction. In the first reaction, as we can see that the aldehyde has been changed into primary alcohol. So this type of reaction is a reduction reaction where we will need a reducing agent. And there are two reducing agents. The first one is sodium borohydride and the other one is lithium tetrahydridoaluminate. So any of these two reducing agents can be added for this question. In the second reaction, we can see that the alkene has been changed into alcohol. This is electrophilic addition reaction, where the reagent required for this reaction will be steam, or that will be water in gaseous form. And the condition for this reaction, it requires concentrated phosphoric acid as a catalyst, where the pressure will be at 6 megapascal and the temperature will be 330 degrees Celsius. So this reagent and also condition can be added to this second question. The question asks for which product in the second reaction will be produced in a larger amount. Since this reaction is an electrophilic addition reaction, it means that it depends on the stability of carbocation, where a more stable carbocation will be produced in a larger amount, and the product from the stable carbocation will also be produced in a larger amount. And the stability carbocation starts from primary, which is the least stable, secondary, and the most stable is tertiary carbocation. Tertiary carbocation, it means that the carbon with the positive charge is bonded to 3 alkyl group. So if you look at this question, if the OH is bonded to this carbon, it means that initially this carbon was a tertiary carbocation. While in R, since the OH is bonded to this carbon, it means that this carbon was a secondary carbocation. So just like we have discussed, tertiary carbocation is the most stable compared to the secondary carbocation. It means that Q will be produced in a larger amount. I hope you guys know the term positive inductive effect. This is when the carbocation attached to 3 alkyl group in this case, because this is a tertiary carbocation, where each alkyl group is an electron donor. So it will donate the electron to the carbocation, which is electron deficient, where it will reduce the charge density of the positive charge. In this next question, we have Q and R added to acidified potassium dichromate. So we all know that potassium dichromate, this is an oxidizing agent. Both Q and R has aldehyde group, which this aldehyde group will be oxidized into carboxylic acid. And in Q and R also we have alcohol group, but the difference here is in Q this is our tertiary alcohol, and in R this is our secondary alcohol. Secondary alcohol can be oxidized into ketone, while tertiary alcohol cannot undergo any oxidation reaction. However, in that sense, both Q and R able to react with potassium dichromate. The color of potassium dichromate is orange, and where it has undergo reduction, so it will change into green due to the presence of Cr3+ ion. Hence, for this question for Q, you will see the orange color turns to green, and it will be the same observation for R as well, because both undergo the same redox reaction. So the question also asks for functional group present in Q and R. In both Q and R, you will see aldehyde oxidized into carboxylic acid, and in R, we have an additional oxidation reaction, which is the secondary alcohol oxidized into ketone. Moving on to the next question, we have PCl5 is added to both Q and R. But the question asks for equation when R is added to PCl5. So for a recap, your PCl5, it will undergo reaction with alcohol or with carboxylic acid. So when it reacts with alcohol functional group, it will change into halogenoalkane in a reaction of substitution reaction. And if the PCl5 react with the carboxylic acid, so it will change into acyl chloride. So in this reaction in R, we have the secondary alcohol. It means that this secondary alcohol will be changed to halogenoalkane. No reaction happening to aldehyde because aldehyde does not react with PCl5. So just copy the whole structure as usual, but change the OH into Cl. So the OH that has been substituted will react with the remaining phosphorus to form POCl3, and obviously HCl will be produced. In the next question, it says that for a reaction of Q and R with PCl5, the sample must be dried first. It means that we cannot have water. So in chapter periodicity, we have learned that the PCl5 will be hydrolyzed in a reaction with water because PCl5 is a covalent bonded molecule. So we want to avoid that reaction because if PCl5 has undergo hydrolysis, it means that there will be no PCl5 to react with Q and R. So now we just need to include an equation that shows a reaction of PCl5 with water and explanation on what will happen if the mixture is not dried first.